Okay. Hello guys, this is Tongzhou. Thank you all for being here today, and also thank Japan, Aurora, and Paul inviting me. So today I'm here to share something about video world models for robot control. So yeah, let's dive in. So I think many people realize that world model has become a buzzword these days, especially in the field of robotics. I think someone told me joke is that if you want to start a new startup and you want to raise funds, then you just say you go to world model. So everything can be a world model. But when we talk about world model, like what exactly is the connection between the world model and robotics? I think this is something I'm trying to discuss with you guys today. So I think there are several different kind of people. Maybe some robotics researchers believe we don't actually need a world model. We just program the robot and ask the robot to do something. That's it. And some world model huge fans will believe, okay, a world model is basically magic. If you try a world model, it can magically solve something which VLA cannot do. And some other robotics researcher maybe believe, okay, world model is a useful tool, and I can use world model to improve my robot policy. So I think there are a lot of different opinions here. But today I just want to share how people have been tried to apply world model in robotics and like what are their pros and cons. So before we start, I want to clarify the scope of today's discussion. So first, I'm gonna talk a specific kind of world model, which is video world model. I'm not gonna talk about, wait, I just realized I forgot to share the screen. Give me 1 second. Okay, cool, let's go back. So we're gonna talk about video world model, which is a specific kind of world model. And I don't think I'm gonna talk about 3D Gaussian splatting today, but 3D Gaussian splatting or NERF is also a kind of world model. Also, I'm not gonna talk about Google Maps, which is literally a world model. I think nothing is more world model than Google Maps, but this is not what I'm gonna talk about today. So, okay, and some disclaimers. So we will talk about a lot of paper today, but this is not an exhaustive list. I tried to cover the well-known ones, but I may miss a lot of also very interesting world model papers. And there are several ways to categorize these video world model papers, but I just went with the one that seemed clearest to me. And I will also mention the pros and cons of the paper discussed in this report, but these are mostly my personal opinions, and they might be wrong. But Japan told me this event is said to be to encourage hot takes, so I think it should be fine. Okay, cool. Let's start. Yeah, this is a figure I made a few weeks ago. And you don't need to take pictures. You can go to my Twitter. I posted it on Twitter. So basically, I try to categorize the way we use video world model in robotics in two dominant paradigms. The first paradigm, I call it using world model as a simulator. The second paradigm is using video world model as a policy. The basic idea is that, just think of those traditional analytical robot simulators like RSXim, Majuco, Manscale, etc. So basically you can encode all the physical laws in the simulator manually, but you can also collect a lot of data to train a learned simulator. And we can use traditional simulator to generate training data, to influence time planning and policy evaluation. Similarly, we can also use these learned simulators to do these things. So this is the first major paradigm. The second major paradigm is that once you train a video world model, basically you can use this video world model as a policy itself. It can directly make the decision for you. Just think of VLA. For VLA, their backbone is a language model, and you can also use video models as a backbone. So I think this is the second major paradigm. So there are also different subcategories under each major paradigm. And for each subcategory, I list a lot of papers. So today, I think this talk is only 30 minutes, so I think I will probably only talk one representative work within each category, but there are a lot of papers doing similar but very interesting things. Okay. So let's first talk about how to use video world models as simulators. The first simple idea is to synthesize data for policy learning. So just think about those traditional simulators. You can collect data and do imitation learning, or you can directly train our agent in this simulator. You can also do the same thing in a learned simulator. So representative example is DreamGen, so which is published by NVIDIA last year. So this idea is that, so assuming you have a text-to-video model, you can prompt this video model to generate some videos, solve the task you are interested in. Then you get a bunch of robotic videos which is relevant to your task. Now you can use inverse dynamics models to generate action labels for these videos. Then you get the trajectories with both video and actions. This becomes your training data for your robot policy. So the idea is very simple. Previously, people use teleoperation or something else to collect the training data. Now you can just prompt the video model to generate this training data for your policy. So it's simple. So I think a key advantage of this kind of approach is that you can easily generate a lot of synthetic experience at a very, very low cost. And because this is basically a simulation, so you can safely simulate real dangerous edge cases. If you want to collect some corner case data on real robot, it can be very costly and very dangerous, but in digital world, it's very safe. You can just do it. So I think this is a key advantage. And I think a con of this kind of approach is that basically all the video generation are open loop. But if we do open loop generation, you know that hallucination is sometimes it's very hard to avoid, because you generate the future video based on your previous generation, and your error will accumulate. So this is something I think very hard to overcome if you do this kind of open loop video generation. Okay, so this is a first representative work. We can use a video model to synthesize training data for your policy. And the second idea is we can use video model for inference time planning. I think Japan told me last week in this event, you guys talk about VJapan too, so I will also talk about it again, because I think this is a very great example. Just assume you learn action conditional video model, which means this video model takes video and action as input and output the video for the next few frames. So this is an action condition video model. Then basically you can search the best action to achieve the goal. So for example, your goal is to pick up an apple. You can search different action sequence and see which action sequence gives you a future which is closest to the goal you want to achieve. And usually when people do this kind of inference time planning, they will use something called model predictive control. Basically, you sample a lot of action sequence and evaluate the outcome of this action sequence. Then you pick the action sequence which gives you the best outcome. Then you execute the first action in this action sequence. You will arrive at a new state. Then you repeat this process. Then eventually you can achieve the goal you want. So this is a basic idea. Once you have a video model, you can run model predictive control in your video model, and this is basically inference time planning. So I think advantage of this kind of approach is that basically it can easily achieve test time scaling, because in language model we observe that test time scaling is very important. And if we want to do something in robotics or video model, this is a very natural way to do that. You can sample more actions, do more plannings, and this is a very good way to use your abundant test time compute if you have it. And I think one con of this kind of approach is that it can be very challenging to fit this kind of heavy computation into real-time compute budget, because think about those reasoning models, it usually takes a lot of time to generate the output you want. And for robotics, the problem might be a little bit more trickier because we want real-time control. So you have to generate some actions before something happens. So it can be pretty challenging to fit this kind of planning paradigm into your real-time control framework. Okay, so this is the second idea, inference time planning. Oh, by the way, if you guys have any questions, feel free to interrupt me. So now let's move on to the third idea. Once we have a learned video model, we can also use it to evaluate your robotic policies. So I think one representative example here is Video Robotics, which is published by who defined a robotics team. So basically what they did is that they have a video model, for example, view. Then they can fine-tune this video model on robotic data to simulate what will happen once you execute some actions. And once you have such a model, you can also evaluate your robotic policy in this learning simulator. The advantage of doing this is that because the simulator is learned, it's not analytical. As long as you have the data, you can simulate a lot of very complex vehicle scenarios. For example, soft body, liquid, or something else where traditional simulation, it's very hard for traditional simulation to handle. I think this is one key advantage. And another thing is that you can never have too many evaluation tools because whenever you want to deploy your policy on real robot, it's always good to test it in some digital simulator first to make sure it's safe. Especially you want to roll out your model to your customer. This becomes more critical. So you can never have too many evaluation tools.
How different is the policy evaluation role model?
Sorry.
In previous slide, we were discussing about the inference time plan, right?
Yeah.
How different is both of them? I think it's similar, right?
It's kind of similar because they are all learned simulators. The idea of the inference planning is to get an action. You want to see which action is a good action to execute on the robot. And evaluation is basically, okay, let's say you have 10 different policy checkpoints. You want to select the best one. You don't know which one is best. Okay, we can evaluate this 10 checkpoints in the learned simulator. Okay, one of them gets the highest score, then I will use this policy checkpoint on the real robot. So it's evaluation. It's not like real-time rollout. So they are both simulator, and the two kind of ideas are actually very similar, but they are still slightly different.
Because at inference time also, the robot or whatever, the embodiment which is going to do the planning, it also needs to select from trajectories, right?
Yeah.
You're going to do the same way.
It's like so inference time planning means you actually want to solve some task now, and while you are solving this task, you can also do inference time planning. But policy evaluation happens even before that. You want to determine which checkpoint you want to use. So this is more like an evaluation tool. But I agree that the ideas are actually very similar. Cool. Yeah, and okay. I think this is definitely very cool. But I think one disadvantage of this kind of approach is that no matter how many data we use and no matter how we scale up the video model, I think video model is always not as accurate as traditional simulations if you can actually correctly implement the traditional simulation. I think this is a disadvantage, but I think but video world model do have advantage on the cases where traditional simulation cannot handle. Yeah. Cool. I think these are three major ideas we use video world models as a learning simulator. So now we can talk about the other major paradigm, which is using video world model as a policy. So as we mentioned, so once you train the video model, you get a good backbone. You can find this backbone to directly make the decision for you. However, we know that the native output of video models are video, they are not actions. In order to control the robot, you need to get robot actions. There are some control signals. So people develop a different method to somehow obtain the robot actions from the video model, and we're gonna talk about it The first idea is that we can just generate the video and action jointly because, okay, we know that the video model generates videos. Why not we just add an action head and just generate both video and action at the same time? And I think one representative work of this idea is Dream Zero, published by NVIDIA like a few months ago. The basic idea is that we know most of the video models are diffusion transformers, so they need to denoise step by step during inference time. And during the denoising, we can actually let the video head and action head output the tokens at the same time, and let them attend to each other and do the denoising at the same time. So this is the basic idea. And if you are not training a diffusion model, you are training like auto-reverse transformer, you can also do similar things. So the idea is that you are not generating one modality before the other modality, you are generating them at the same time. So I think the advantage of this kind of idea is that you can leverage the rich prior of the pre-trained video model with minimal architecture changes. Because we know once you pre-train your video model, it actually already learned a lot of knowledge about this physical world. It knows how the object can move, how people interact with this object. And most of this knowledge can be potentially preserved in the video action model you train. And I think this is the advantage. And I think the con of this kind of approach is that because at the end of the day, video models are not pre-trained to predict actions, they are pre-trained to predict videos. You need to add this action head during your post-training stage. So it's unclear what's the best way to do it, and it's also unclear whether there will be any disadvantage if you add in additional modalities in the post-training stage. So I would say this is more like an open question right now. So this is jointly generating video and actions. And some other paper also tried a different idea. Basically, so in this paper, they no longer generate videos because they already have a video model trained. They basically just use it as a backbone and extract some visual representations with this video model backbone. One representative work of this kind of idea is VPP, Video Prediction Policy, published by Tsinghua University. The basic idea is just like I mentioned. So they use a pre-trained video model backbone to generate the representation. So they don't do multiple denoise steps at all. They just do one forward pass. Then they will get visual representation, which encode a lot of information about the current observation. Then you, with this visual representation, we train another action model to map this visual representation to an action. And that action model can also be a denoising diffusion model. And you run a diffusion process on that action model. If your action model is not as large as the video model, this denoising process can be much faster. So I would say the key advantage of this kind of idea is that because you no longer need to run multiple denoising steps on the giant video model, so your inference will be much faster, which makes real-time control much easier. On the other hand, it also remains unclear that if you don't do the full denoising process, we don't know whether you can actually fully utilize the potential of the pre-trained video model. So I think there's no free lunch. Okay. So yeah, that's another idea. You basically just run one step forward pass and use the representation to learn actions. The third idea is actually more straightforward. So basically, you just let the video model do what it's trained to do. So video model just takes the past observation and generates future videos. Then we train another video to action translator to translate the generated videos into actions. I think there's a pioneer work on this line of research, which is called UniPy, published by Google a few years ago. The basic idea is that they basically train a video diffusion model to predict what should happen next. And they also have an inverse dynamics model, which is basically a video to action translator. This inverse dynamics model takes the predict video as the input and output the actions. and we use this action to control the robot. You may find this kind of idea very similar to the Dream Jam paper we mentioned like 10 minutes earlier. The key difference here is that in Dream Jam, they use the generated video and actions as the training data to train another policy. But here, the video model plus the inverse dynamics model itself is a policy. They do not use the data to train another policy. The system itself is a policy. So I think the key advantage of this kind of approach is that it allows the video model to do exactly what they were trying to do, which is video generation, which makes a lot of sense to me. But there are also disadvantages because video models are very slow. It takes a lot of time to generate videos. So usually, at least a few years ago, people usually do this kind of video generation and translation in an open loop manner. Open loop basically means for a specific task, you come up with a plan up front and through this plan to the robot and never change the plan again, no matter what happens. So intuitively, you will find this is actually not a very good idea. So because it often lead to a hallucination because you need to further generate the videos based on your previously generated videos. The errors will accumulate too. No matter what happens in the real physical world, your robot cannot react to it. So I think this is a key disadvantage of this kind of open loop generation approach. However, I think recently some paper already achieved closed loop video generation plus video to action translation. There are a couple of works, including DVA from Rhoda and embodied from Alibaba and Mimic Video from a company called Mimic Robotics. The idea is basically same as the previous line of research, but they basically convert this kind of system into a closed loop system. There are a few very critical components you need to implement in order to make this closed loop. For example, you have to train a causal video model, because if your video model is not causal, if it uses bidirectional attention, that means every time you run the inference, you cannot utilize the KB cache you generate last time. Basically, you need to recompute everything. This way, the inference will be very slow. But if you train a causal video model, then you can enable KB cache. It will reduce your inference compute by a lot. So this is a very important component you need to implement. And also you need to implement a lot of inference optimization tricks to make sure your video model can run fast enough to achieve real-time control. Yeah. So I think the key advantage of this kind of approach is very clear, because it's closed loop. It avoids hallucination. It can react to what happened in the real world. And the con of this kind of approach is basically, okay, you definitely need to train a causal video model, which is non-trivial, and you need to implement a lot of inference optimization tricks, which is also non-trivial. But if you can do it, I think this will be very good and very promising. Any questions?
When you say inverse dynamics model, how are we diversifying the dynamics for different robots? Because whether it remains same general actions versus video model, I'm just curious, how can we diversify the different manipulator tasks, different manipulation robots?
Okay, so your question is how do we diversify the data for inverse dynamics models? Okay, so first, based on my empirical observation, you actually don't need too much data to train inverse dynamics model, because what the inverse dynamics learn is to translate the video of robot motion into the real robot actions. So that means even if your robot are doing the task A, the motion can definitely be transferred to task B. For example, the motion of pick up a pen and pick up an apple can be very similar. And as long as you train, your training data covers this kind of motion, and your inverse dynamics model learns how to convert to this kind of motion video to the robot actions, it can naturally generalize to, it can usually generalize to other similar motions. And also, you don't need very high quality data to train this, because For example, if you want to train a robot policy to do some tasks, you definitely want good data, high quality data, which can complete this task very well. But for inverse dynamics model, you can use a lot of different data. It can be television data, or evaluation data, or even like just play data, or some random movement data. All of these can be very useful for training inverse dynamics model.
Isn't it user friendly for the robot and the vector? What is how? Because each robot will have its own different kind of end effectors, different degrees of freedom for like 6 degrees, 7, 9. So how does the inverse dynamics work for those kind of scenarios?
I think usually, okay, that's a very good question. I think the safest way is definitely for different robots, you collect data on different robots and train different inverse models. But if you merge all the data set and train a unified inverse dynamics model, I don't see a reason it cannot work.
Okay.
But my point is that empirically we find that you don't need a lot of data to train this inverse dynamics model. So anyway, it works. Yeah, it won't be too deep. It's definitely not the bottleneck of this system. The hard part is the video model, not the inverse model.
So how does the IDMs handle occlusions?
Sorry?
How does the IDMs handle occlusions?
Local motion.
Occlusions.
Occlusion.
Oh, okay. Let's imagine such a scenario. If we want to train a humanoid with textured hands, and let's say I'm the humanoid, I'm doing something here, and if I only have a camera here, then basically I can see nothing. There's no way I can train this inverse dynamic model to predict my action, right? So I think the key idea is that you do need avoid occlusion by engineering design. For example, you can add a camera here to clearly see how my hand moves. And I think in practice, people usually use 3 cameras you own by manual, 1 hand camera and 2 rest camera. I think in most of cases, it's enough to capture it can capture enough information for you to translate the video to actions. But in the case that the motion is actually blocked, actually occluded, I don't think you can do it.
Yeah, what do you think of like non-static environments where you might have different movements, but at the end of the day you want to capture the inverse dynamic model of the robot or embodied view interface. But there might be other, let's say, in an environment, some cats are going around, running around, right?
If some kids are going around, I think that's part of the background, right?
Yeah, but how do you explicitly tell your model that, okay, just ignore the background and do your thing?
I don't think you need to do it, because when we train the inverse dynamics models on the data with something moving in the background, the model will naturally learn. Okay, I find there's a lot of video. In some videos, the backgrounds are moving. In some videos, the backgrounds are not moving, but they all translate to the same action. The model will naturally learn. Okay, the movement in backgrounds are not relevant to my actions.
Yeah, because sometimes I think people like to give this interesting example where you have an object where the robot is trying to reach, right? Because let's say someone is pushing the object towards the robot. So in this case, is the inverse dynamic model confused or?
I don't think so, because if someone pushes the object, it does not change your robot action, right? It changes what you observe, but it doesn't change the supervision. The supervision of the inverse dynamics model in robot actions. I think as long as you have the diverse data, I don't think it matters. Yeah.
Sorry, just want to get back on this thing. If you jointly diffuse the 2 things together, where you have like proprioception and video jointly diffused, then the occlusion should not be a problem, right?
Can you answer the question again?
Yeah. So in the previous slide, you were talking about how you had joint diffuse models, not this one. You were diffusing a few modalities together, and you were generating not just the video but also the actions at the same time. So if you do that in the last case, you can. It's fine if things are occluded, because the other stream of information will still know exactly what the actions do are.
I think not necessarily, because when we say the actions and videos are denoised together, we're talking about the output. But all the modality will always be your input. Even if we only denoise one of the modalities, all other modalities will be your input. You can also attend to those tokens, but you are just not denoising them at the same time. So I think the information they got are the same. So when we denoising the actions, we also see all the visual tokens. We just don't denoise them at the same time.
Right.
Does this make sense?
Yeah. I guess you should denoise them together then.
I think that's a design option. Yeah. I think my philosophy is that because the video model is trained to predict video, so we just let it do what it's trained to do, and we just train another model to translate video to actions, and we empirically verify it. It's not very hard to train this translator. Yeah. Yeah, but I would say this is still an open question. People can have different design choices.
Do you think most of the failures are coming from the video backbone, or is that inverse kinetics translation?
Yeah, empirically, I will say that's true. If the system cannot complete something, it's usually due to video model rather than the inverse model. Because think it this way, the problem inverse model need to solve is basically a translation problem. Just think of you need to translate the English to French. In this case, in our case, the English is basically video, the French is the action. So this is a very constrained problem. As long as you have enough parallel corpus, it's almost guaranteed you can solve this problem because you don't need to make any decisions yourself. But for the video model, it's an entirely different problem. The video model need to make the decision. It need to decide how the robot should move and how the world should change. And there's a lot of possibilities. But for the translation problem, there's just not a lot.
Model. We're only evaluating the video generation quality, a little bit too strict for that, because that requires the world model to pay attention to all the details, even not policy related, while better scaffolding the policy will be something people more care about. Just want to know what you think about is a good systematic set of practices that examine if a world model is good.
Yeah, I think this is a very good question. Basically, it's basically asking how do you evaluate a pre-trained video model. I think honestly, I don't have a very good answer for that. I think at Rhoda we are also trying to build a lot of metrics which can reflect the performance of the pre-trained video model, but I don't think I'm allowed to discuss this metric here. But from another perspective, I think a very naive way to evaluate it is just to portray your video model to the downstream application you care about. If you pre-train video model get good performance on this downstream application, that is a good video model. Yeah.
Is it policy evaluation or data synthesizing or policy guidance?
Most valuable.
Yeah, the most beneficial use case for video generation model. Like a policy evaluation or data synthesizing or policy guidance or something.
I think they are all complementary, right? They are not competing. Why can we do them at the same time? But I feel the benefit of video model is that it's so versatile. You can post-train it to do a lot of different things. You can post-train it to be a simulator to evaluate your policy. You can post-train it to be a policy, or you can post-train it to be a value function or something else. It's so versatile. I think that's very cool. Yeah. You don't need to constrain yourself to one single use case. You can do all of them, right?
Would you say?
In existing papers or engineering experience that can help us reduce the inference time.
Yeah, I think as I mentioned, from the model perspective, if you can do compilation, it makes the model produce less precision of numbers, and you can also do diffusion denoising. For example, you can try to make the denoising path denoising ODE straighter, so you can use less denoise steps, and you can also do model size dissolution. For example, rather than you have a huge giant video model, you can distill it to a smaller model. These are all like model size optimization. And from the engineering side, you can also do a lot of things. As I mentioned, you can do kernel fusion, product graph optimization, and there's a on list of optimization you can do, but these are all engineering tricks. Estimate the headroom. If you want to underestimate how much speed up you can get by optimizing your